All right, in this example, we are going to cover the basic idea behind a velocity selector. So we are going to be tackling the example on page 37. So on page 37, we are shown a diagram of a particle that is moving in the positive x direction. So let's read the question. So the net force on a charge moving with a velocity v is 0. Find the speed of that charge. Now, by the way, it's a bit hard to draw this diagram. It is in 3D. I will draw a 2D vector diagram and it will be roughly equivalent. Before I start solving this problem, we need to look at the basic idea behind the velocity selector. So the idea behind a velocity selector is if the electric field and the magnetic field are just right, only particle with a certain velocity will not be deviated, all right? So how can we make it such that the electric field and the magnetic field do not deviate a charged particle at a given speed? Well, it means that the force acting on this particle has to be 0. So if we look at the force, if we look at the force over here, it is equal to the Coulomb force, so which is the charge multiplied by the electric field, plus the magnetic force, all right? In order for the force to be 0, the vector, the Coulomb force, need to be equal and exactly in opposite direction as the magnetic force, all right? Now, so that means we have two conditions here. Both vector has to point exactly in opposite direction, and both vector has to have exactly the same magnitude. So from the point of view of the magnitude, we have the electric field, so on both sides here, we can cancel out the mass, by the way, because they both share the same mass. We got the electric field has to equal the magnitude of the magnetic force. So the velocity multiplied by the magnetic field multiplied by the sine of the angle between these two. And basically the magnitude of these two forces will be equivalent when the velocity is equal to the electric field divided by the magnetic field. And note this is the angle between the velocity and the magnetic field in nearly all the question we're going to consider involving a velocity selector. This will be 90 degrees, all right, so it will become 1. All right, we're given the electric field in our problem. It is 300,000 voltmeter. We're given the magnetic field. It is 0.1 Tesla. All right, so on the diagram, which I said at the beginning is a bit hard to draw, we have three vectors, and we can see them as such. We have the velocity vector pointing in the x direction. We have the electric field vector pointing in the positive y direction, and we have the magnetic field pointing out of the board in the positive z direction. All right, so first let's test that these two forces are exactly in opposite direction. So we point our finger toward the velocity vector, so in the positive x. We curl toward the magnetic field, so in this case the magnetic field is toward the camera, and my thumb is pointing in the direction of the magnetic force, so it is pointing downward. And so it is pointing in the opposite direction as the electric field, and the electric field is pointing in the same direction as the electric force. Therefore, they are exactly in opposite direction, and if their magnitude is equal, that means they can have an added net force of 0. So this will happen when the velocity is equal to the electric field divided by the magnetic field. Now note there's sine theta here, but we can clearly see on the diagram that they are all perpendicular. So the sine is sine of 90, become 1. So we input the electric field divided by the magnetic field, and we get a velocity of 3 multiplied by 10 to the power 6 meters second. So when the particle is going at 3 multiplied to the power 10 to the power 6 meter per second, the net force on that charged particle become 0. All right, so in the next video we are going to solve some more example involving that concept over here. All right, so let's move to another example.